Welcome to qnawire.
Our objective is to determine the value of n for a particle in a one-dimensional infinite potential well, find the energy of the n+1 state, and determine if quantum effects would be observable. First, we need to find the energy levels of a particle in a 1-dimensional infinite potential well. The energy levels are given by the formula En equal to n2 pi 222 L2, where En is the energy of the n-th level, n is an integer, is the reduced Planck constant, m is the mass of the particle, and L is the width of the well. Given the mass m equal to 15 and g equal to 15 times 10 - 6, the width of the well L equal to 1.2 cm equal to 1.2 times 10 - 2, and the energy En equal to 15 and j equal to 15 times 10 - 3j, we can solve for n. 15 times 10 - 3 equal to n2 pi 220 to 15 times 10 - 6 and 0.2 times 10 - 2. To solving for n, we get n equal to square root 15 times 10 - 3 times 2 times 15 times 10 - 6 times 1.2 times 10 - 2 2 pi 2 2 using 1.54 times 10 - 34j times s, we find n 1.22. Since m must be an integer, we round up to the nearest integer, n equal to 2 now. We can find the energy of the n+1 state. En+1 equal to n+1 2 pi 222 L2 equal to 3 2 pi 220 to 15 times 10 - 6 and 0.2 times 10 - 2 233.75 times 10 - 3j. So the energy of the n+1 state is En+1 33.75 mj. For part C, we need to determine if quantum effect would be observable for this particle. One way to do this is to compare the energy difference between two consecutive energy levels of the thermal energy of the particle at room temperature. The thermal energy is given by kBT, where kB is the Boltzmann constant and T is the temperature. At room temperature, D 300 K and kB 1.38 times 10 - 23 J/K, so the thermal energy is kBT 4.13 times 10 - 21 J. The energy difference between the n equal to 2 and n equal to 3 states is delta E equal to E.